This looks like a torture device. I don't want to scrape my face with something 19th century Irish gangsters used to kill each other with.
So how do you shave with a double-edged safety razor?
Once considered a tool that demanded daily maintenance, significant skill, and a steady hand simply to operate safely, the razor blade by the early 20th century was about to become something almost no one had anticipated. A mass-produced, disposable product that any person could use at home without training, sharpening, or prior experience. It was a small steel rectangle. Manufacturing it to the required standard was anything but small. This video will take you inside razor blade manufacturing in the 1910s to uncover exactly how thin steel was transformed into one of the most precisely made consumer products of its era. Why the process required simultaneous advances in metallurgy, heat treatment, and grinding technology, and how a product small enough to hold between 2 fingers changed personal hygiene for billions of people permanently. Right now, let us explore this remarkable manufacturing story together. In the decades before disposable razor blades reached the market, the standard shaving tool for most men was the straight razor, a single piece of high-carbon steel ground to a fine edge, capable of lasting years when properly maintained. Before each use, the blade required stropping on a leather strap to realign its microscopic cutting edge. Every several weeks, it needed honing on a sharpening stone to restore metal that stropping could no longer recover. Neglecting either process produced a blade that dragged, scraped, and cut skin rather than hair. As industrial cities expanded during the late 1800s and working hours increased, the time and skill demanded by straight razor maintenance became a growing inconvenience for a significant portion of the population. The market for a simpler alternative was not difficult to identify. What was difficult was building one. A blade thin enough to be disposable also had to be hard enough to shave effectively, uniform enough to be manufactured in the millions, and consistent enough that every example performed identically to the last. Requirements that would take years of engineering effort to meet simultaneously. That challenge would soon lead to one of the most technically demanding consumer manufacturing processes of the early 20th century. The commercial framework for the disposable razor blade was established by King Camp Gillette, who filed his foundational patent in 1901 and began selling safety razors with replaceable blades in 1903. Gillette's concept was straightforward in principle: a thin stamped steel blade that could be discarded when dull rather than resharpened. Translating that concept into manufacturable reality required the work of engineer William Emery Nickerson, who spent approximately 6 years developing the machinery, steel specifications, and heat treatment processes capable of producing blades at commercial scale. The central engineering challenge was a direct contradiction built into the product's requirements: a blade thin enough to be economically disposable, typically between 0.1 and 0.15 millimeters in the 1910s, lacked the structural rigidity to resist lateral forces applied during shaving without a precisely engineered support structure, and a hardness level that thin steel was not easy to achieve without simultaneously making it brittle. Interestingly, solving that contradiction required advances in steel selection, stamping precision, heat treatment sequencing, and edge grinding that did not exist when Gillette first proposed the idea. By the early 1910s, those advances were in place, and the manufacturing process that resulted was among the most technically demanding in consumer goods production of its period. From that point, every blade began the same journey, starting as raw steel and ending as a finished cutting tool ready for millions of daily users. Every razor blade manufactured in the 1910s began its journey as a coiled strip of high-carbon steel, typically containing between 0.6 and 1.0% carbon by weight, a specification that allowed the metal to be hardened sufficiently through the heat treatment to hold a functional cutting edge. Stainless steel alloys capable of resisting corrosion while maintaining adequate hardness were not yet available for blade production, leaving manufacturers dependent on carbon steel despite its well-known vulnerability to rust in damp conditions. Massive coils of steel strip arrived at the factory already rolled to a carefully controlled thickness. Even minor variations, deviations of more than a few thousandths of a millimeter, produced blanks that behaved inconsistently during hardening and grinding, undermining the dimensional uniformity the entire production system depended on. At this stage, the strips moved through solvent cleaning baths to remove rolling oils applied during steel production, ensuring no surface contamination interfered with subsequent heat treatment or edge finishing. Once cleaned and verified against thickness specifications, the prepared strips entered the stamping line, the first stage where steel began taking the recognizable form of a razor blade. The prepared steel strip fed continuously through a series of stamping presses, each performing a specific operation in a defined sequence. The first press punched the blade's center slot and aligned holes, features that allowed the finished blade to seat precisely within the razor's clamping mechanism, correctly positioned relative to the cutting head. Tolerances on hole placement were held to within approximately 0.05 millimeters, because any misalignment translated directly into blade movement during shaving, compromising both comfort and safety. Subsequent stamping operations separated individual blade blanks from the continuous strip and formed the blade's overall profile. At this stage, the blanks were geometrically correct, but metallurgically soft, retaining the relatively ductile properties of their annealed condition, making them straightforward to inspect from stamping defects before the irreversible heat treatment process began. Blanks showing tears, burrs outside acceptable limits, or hole placement deviations were removed from the line at this point. One fascinating detail is that catching defects here costs only the blank itself. Catching them after hardening costs considerably more time, energy, and material, something no production manager in the 1910s needed explaining twice. Once accepted, the blade blanks moved directly into the hardening furnaces for the most critical stage of their journey. Accepted blade blanks entered continuous hardening furnaces, where they were heated to temperatures between approximately 760 and 800 degrees Celsius, the range at which high-carbon steel undergoes the austenitic transformation that enables subsequent hardening. After holding at the target temperature for a controlled duration, the blanks were quenched rapidly in oil, dropping their temperature within seconds and locking the steel's internal structure into its hardened, martensitic form. Hardened blades at this stage reached Rockwell hardness values between 62 and 65 HRC, extremely hard, but also dangerously brittle. A blade in this condition would fracture rather than flex under the stresses of normal use. The blanks immediately moved into the tempering furnaces, where they were reheated to temperatures between approximately 150 and 200 degrees Celsius for a controlled period. Tempering reduced internal stresses accumulated during quenching, lowered brittleness to acceptable levels, and brought final hardness down to a range of approximately 58 to 62 HRC, hard enough to hold a sharp edge through multiple shaves and flexible enough to survive clamped into a razor without fracturing. Throughout both heat treatment stages, blade flatness was monitored carefully, as thin steel at elevated temperatures had a reliable tendency to warp in ways that no amount of subsequent grinding could fully correct. Once the tempering cycle was complete, The blades emerged from the furnaces ready for the operation that would finally make them functional cutting tools. The hardened and tempered blade blanks entered the grinding department, where large precision grinding wheels, dressed to maintain consistent profiles, worked both cutting edges of each blade simultaneously. Material was removed at controlled rates to produce the double bevel geometry that defined the safety razor blade's cutting action. Edge angle consistency was critical. Variations of even 1 degree across the grinding wheel's working surface produced edges that felt noticeably different during use, being sharper on one section than another or harsher on one side than its opposite. After primary grinding, the blades moved through progressive stropping and honing stages using increasingly fine abrasive and leather surfaces, removing microscopic burrs left by the grinding wheels and refining the edge to its final sharpness specification. At this stage, the completed edge was sharp enough to cut individual hairs cleanly on contact, a fact that kept the inspection department handling thousands of blades daily, consistently and professionally attentive. Every production batch underwent systematic inspection before release. Workers examined blades for warping, edge irregularities, hole placement deviations, and surface defects. Blades failing any criterion were rejected entirely, a quality standard that was commercially essential given that the disposable blade's entire market proposition depended on consumers trusting that every blade in every package would perform identically to the last. Accepted blades received brand identification printed or embossed directly onto the steel surface before being individually wrapped in wax paper, a moisture barrier that provided meaningful but imperfect protection against corrosion. Wrapped blades were packed into small cardboard cartons, typically containing 3 to 12 blades, and prepared for distribution. By the mid-1910s, the United States military had adopted the safety razor for standard issue, introducing disposable blades to millions of soldiers serving across Europe during the First World War. Military procurement contracts drove production volumes into the hundreds of millions of units annually, establishing manufacturing infrastructure and consumer habits simultaneously. Most soldiers continued using the format after returning home, permanently shifting the global shaving market away from the straight razor within a single generation. Every razor blade produced in those factories, and every blade produced across the century of manufacturing that followed, traced its design logic, its metallurgical specifications, and its precision process requirements directly to the engineering work completed between 1901 and 1910. A product small enough to disappear between 2 fingers, demanding some of the most exacting manufacturing standards its era had ever attempted, used billions of times daily without a second thought, and discarded just as quickly, which was, of course, entirely the point.